Hey, what's up, everybody? Welcome to the Chapter 5 guided assignment. I'm just going to walk through these, so hopefully they will make sense, and you can learn the concepts from the chapter. So let's take a look at the first question. It says 3 students scheduled interviews for summer employment at the Brookwood Institute. In each case, the interview results in either an offer for a position or no offer. Experimental outcomes are defined in terms of the results of the 3 interviews. So it doesn't say anything about like if one person gets a job, then the other 2 can't, or that their chances are diminished. So just it sounds like that there's equal opportunity for each of the 3 students to get the job. So what are our potential experimental outcomes? So you can look at the choices they give us. We know there has to be a situation where there's 3 no's and 3 yeses, and then no, yes, etc. So like this one, how it has only 2 options, that one can't be right at all because there are 3 different people interviewing. And so there will be 3 potential outcomes for each of our, or 3, I guess, items in each potential outcome would be a good way to put that. And then we can see this one doesn't offer us all of the options. And so that's going to be all of the potential experimental outcomes. So B says, let X equal the number of students who receive an offer. Is X continuous or discrete? Well, continuous variables typically include all numbers in a set, including like decimals and things like that. In this case, since all you can get is a yes or a no, and the number of students is 3, we can either have 0 yeses, 1 yes, 2 yes, or 3 yeses. That's really the only options. And so this is what's called a discrete variable because there's no in between. You can't have 2.5 people getting an offer. All right. So then finally for C, show the value of the random variable X for each of the experimental outcomes, where X is the number of yeses. So Y equals yes, the student receives an offer. No equals no, they don't. If your answer is 0 or the experimental outcome does not occur, enter 0. So in most of these, I would say we just count the number of yeses. But in these first 4, you can see there's only 2 experimental outcome or 2 items in each experimental outcome. And those can't happen, right? Because there's 3 people, we have to have 3 items in there. So we're going to put 0 because these don't happen. And then for the rest of these, we'll just count the number of yeses. So there's 2 yeses. So the value of X is 2. 2, 1, 1. And that's it. That should be right. Let's double check, make sure I didn't make any mistakes. I do that sometimes. But on this one, we got them right. So there's the first question. Let's move on to the next one. All right. A technician services mailing machines at companies in the Phoenix area. Depending on the type of malfunction, the service call can take 1, 2, 3, or 4 hours. The different types of malfunctions occur at the same frequency. So that tells us that there's not a higher likelihood of it being a 1-hour service call or being a 4-hour service call, that they all have the same frequency. So develop a probability distribution for the duration of a service call. So if there's 4 options and they each occur with the same frequency, then it's just going to be 0.25 for each of them. Or there's a 25% probability that it's a 1-hour service call, a 25% probability that it's a 2-hour service call, 3, 4, etc. So we add those all up, they add up to 1. So then it asks us, well, which of the following probability distribution graphs accurately represents the data set? And it would be the one where each of the items, 1, 2, 3, and 4, is at 25%. So this one's out because some of them are different. And this one, it's less than 0.2. So we're going to say number 2. And then it says, consider the required conditions for a discrete probability distribution shown below. The first, f of x is greater than or equal to 0. So for each of these, our f of x is greater than or equal to 0. So we'll say equation 5.1, yes, it satisfies that. The second one, 5.2, is that the sum of f of x is equal to 1. So if we look at the sum where we added them all up, it is equal to 1. So we'll say yes, it also satisfies that. So we've got a discrete probability distribution. So what's the probability a service call will take 3 hours? Well, we figured it out right here, 0.25. So there is a 0.25 probability that, given all of the rest of the information we've already looked at, right, that there are 4 potential outcomes and they all have the same frequency, then there's a 0.25 probability. Finally, a service call has just come in, but the type of malfunction is unknown. It's 3 p.m. and service technicians usually get off by 5 p.m. What's the probability the service technician will have to work overtime to fix the machine today? So what we're really saying is, what's the probability that it is? Because if it's a 1-hour job, won't have to work overtime. A 2-hour job, still won't have to. They'll get done by 5. So we're saying, what's the probability that is either a 3 or a 4-hour job? So if it's a 0.25 that it's 3 and a 0.25 that it's 4, if we just add those together, we'd say there's a 0.5 probability that the technician would have to work overtime. All right, so it looks like we're good on that one. Let's take a look at number 3. All right, the following table provides a probability distribution for the random variable y. Okay. And so this tells us that for the value y, there is a 0.2 probability of that occurring, 0.3 of 4, 0.4 of 7, and 0.1 of 8. So they want us to calculate the, or compute is their word, the expected value of y to 1 decimal. So I'm just going to bring an Excel spreadsheet up here. So we're going to go y and f of y four 0.3, 7.4, and 8 and 0.1. All right, so we just have that same information from this little table put into Excel now to make our life a little easier. All right, so to find our expected value, all we're going to do is we're just going to multiply the value of y times the probability of that. We can do that all the way down, take the sum of it, and that's our expected value. In essence, what we're saying is, if there's a 0.2 probability of 2 and a 0.3 probability of 4, etc., we just multiply them out and we're finding a weighted average here. But using, and since the probability adds up to 1, we don't have to do any dividing. We could say 5.2 divided by 1 is 5.2. But really, the expected value is just the value times the probability of getting that value, and then take the sum of all those values. All right, so then to compute the variance, that's a little bit more work, because the first thing we have to do is find the mean. And it's no simple, I mean, there is with a function, I'll show you here, but like the mean is, again, like a weighted mean, right? Where we have to take the values of y and then the values of the probabilities. We use the sum product function, which in essence means take this times this, and then this times this, this times this, this times this, and then add them all up. So there's our mean. No surprise there, right? Because guess what? That's exactly what we did right there. I just wanted to show you some product. All right. So now that we know the mean, what we're going to do is we're going to find the value of y minus the mean. And I'm just going to use the little dollar signs here so that I can use the fill tool and it doesn't have any problems for us. So there's our y minus the mean. And then the square, or that squared. And again, I could have skipped steps, but I just want to show you how this whole thing works out. Right, I could have used some product again and just put this, I could have done the squared here, all of those things, but I think sometimes this helps us see it better. So we're going to square the difference between y and the mean. And if this weren't weighted by these probabilities, we would just sum those up and that would be our variance. But now we've got to do one more step, which is to do this number times the weight. Okay, so I'm just going to say this equals the y minus the mean squared times the probability weight. And we'll take the sum of those, and that'll give us our variance. Check that. Just because that number feels weird to me, but it's not. And then my standard deviation, if I can type correctly, is always just the square root of our variance. And it wants 2 decimals. So there we go. So remember, all variance is the difference between each value of y and the mean squared. And then in the case of where we have a weight, either probabilities or we have a weighted average, it's that squared difference between the value of y and the mean times the weight. And then we just take the sum of those, and that gives us our variance. And since that's in squared units, which isn't very helpful to us in real life, then we can take the square root of it, and that gives us standard deviation, which is more helpful because it's back in our whatever units we were using. All right, so that was number 3. Let's take a look at number 4. All right, so according to a 2018 survey by Bankrate.com, 20% of adults in the United States save nothing for retirement. Suppose that, man, that's 20%, 1 in 5. Suppose that 15% or that 15 adults in the United States are selected randomly. Is the selection of 15 adults a binomial experiment? Explain. So we'd say this selection is a binomial experiment because the adults are selected randomly. And P, or our probability, does not change from trial to trial. And the trials are independent of each other, meaning one trial doesn't affect the probability of the next trial. And there are exactly 2 outcomes possible. Either they do save or they don't save. So all of those things tells us by definition, this is a binomial probability distribution. So one thing we can do with Excel, if we're not sure how to move forward, we know we have a binomial distribution here. So we can come into Excel and use the function binom.dist. And when we do that, we can see the arguments or the information that we're going to have to put into Excel to use the binomial distribution. So we know we're going to need the number of successes, the number of trials, and the probability of success. So once you do that, we can just set up our own little calculator. I'll explain true false here in a second. All right, so let's just take a look at this. So what we're saying is, so the first question is, what is the probability that all of the selected adults save nothing for retirement? So we have to decide what a success is. Usually the problem kind of tells us. So it says 20% of adults save nothing for retirement. And then they're asking us, what's the probability that these people save nothing for retirement? So even though it's weird to call it a success that people don't save anything for retirement, recognize that we're not making a value judgment here. We're just making a mathematical sort of query. Okay. And so I'm going to say, all right, so the first question is asking, what's the probability that all of the adults save nothing for retirement? So I'm going to say that represents 15 successes out of 15 trials. That I asked 15 people, and all 15 of them say, hey, you can't spell probability. And they say, no, we don't save anything. Okay. So our probability of success is 0.2, meaning it's likely that for every person we ask, there's a 20% probability they'll say they don't save anything, and an 80% probability that says they do save some. And then finally, we get to this true false part. And true false is how Excel defines if we're taking a cumulative distribution, so we're looking at all of the potential values, or if we're just looking at exactly a value. So in this case, we're going to say, what we're asking is it 50? How do I put this? The best way to put this is, what's the probability that exactly 15 people say this? Okay. So when we say false, we're saying, what's the probability that exactly this number occurs? And when we say true, we're saying, what's the probability that this number or less gives us this response? Okay. So now I'm going to call this the probability of success. That way we can differentiate this from our answer, which is our probability. All right, so we're going to use the function equals binom.dist, number of successes, comma, trials, comma, probability of success, comma, and then, oops, I hit a period there. And then our true false. So here we can see we have some crazy small number, 3.27. This little e means exponent, or times 10 to the negative 11th. So if we only round to 4 decimals, then the probability that all 15 of them, that nobody saves, or that all 15 say they don't save, is 0 to 4 decimals. We'd have to get out to, to 11 decimals before we start seeing something. So very little chance that nobody that we ask is going to save. So the second one says, what's the probability that exactly 5 of the selected adults save nothing for retirement? So now I'm going to put 5 for my successes, and I'm going to leave true, false, false, because false means that we're looking for an exact number. True means we're looking for that number or fewer. Okay, that's how Excel returns this answer. And I'm going to let Excel do the work for me on rounding so I don't make a silly mistake. 0.1032. Or about a 10%, 0.1032 probability that exactly 5 people save nothing. And so here's our last one. It says, what's the probability that at least one of the selected adults saves nothing? So right now, if I were to just put 1 in here for successes, that would give me the probability that exactly one person saves nothing. So that's not going to give me the answer I want. If I were to put 1 and then change this to true, now it's giving me the probability of 1 or fewer people. I need 1 or more, okay? So what I have to do, this is really the probability with true in there, it's the probability that it is this number or less. And so I need the probability that it's greater, right? At least 1. And we know that with probabilities that all of the data adds up to 1. So if I say this equals 1 minus this probability that it is less than, that's going to give me the probability that it's greater. But I still got one more problem here. Right now, the way this is set up is it's giving me, so this is the probability that 1 or 0 people, right, answered that they don't save, which means this is the probability that 2 or greater, but it's asking me for at least 1. So what I have to do is put 0 on my successes here. So now this probability shows the probability that 0 people responded that they save nothing for retirement. And this gives me the probability that 1 or greater. And that's what fits with at least 1. So the probability that 1 or more, at least one person, says they save nothing for retirement is 0.9648. So very likely that we're going to get at least one person who's going to respond and say they don't save anything for retirement. So I hope that made sense. I was trying to kind of talk through the logic of how we set up our little calculators here. All right. Let's look at number 5. Airline passengers arrive randomly and independently at the passenger screening facility at a major international airport. The mean arrival rate is 10 passengers per minute. So when we're looking at a discrete probability distribution, okay, and it's presented to us in terms of a per, like 10 passengers per minute, or 20 hamburgers are made per hour or whatever, then we're looking at a Poisson probability distribution, or Poisson or something. I don't speak French, but it's something like that. Anyway, so again, when we're not sure exactly how to proceed, we can always put in the distribution, the function in Excel, and it will tell us the arguments or the information it needs. It needs a value of X, it needs a mean, and it needs to know whether it's cumulative or not. Again, cumulative meaning that value and fewer if it's true, or exactly a given value if it's false. So that's the information our Poisson distribution is going to need. Whoops, let me just get rid of this for a second. So we're going to need a value of X. We're going to need a mean. And we're going to need to know the cumulative or the true false. All right, so this tells us the mean arrival rate is 10 per minute. And then we have to look here and say, compute the probability that no arrivals in a 1 minute period. That would mean X of 0 out of an average of 10. And we're looking for exactly 10. So we're going to say false. So now we can figure out our probability, which is Poisson.dist X mean and cumulative. Oh, I didn't hit a comma, I hit a period. All right, so that's 4.53999 times 10 to the 5th. This says to do it to 6 decimals. So that means if we, let's take it off of exponent and just have it show us. So to 6 decimals, that's 0.000045. Am I 5 there? Yeah, 0.000045. Sort of silly, they tell us to do it to 6 decimals, but we can only see 5 active. Yeah, so it's kind of weird. All right, the second one, compute the probability that 3 or fewer passengers arrive in a 1-minute period. So now, since we've got a good calculator set up, all we have to do is change x to 3. But if we're on false, right now it's telling us exactly 3 passengers. So if we want 3 or fewer, we'll change that to true. And now that's going to give us the cumulative function, meaning not just looking at one given value of x, but at 3 or fewer, 3, 2, 1, or 0. So this one, it wants it to 4 decimals. So 0.0103. The probability there are no arrivals in a 15-second period. So this one's a little tricky because, again, it sounds like we're going to go back to 0. But also, we have to recognize that up here, our arrival rate was 10 passengers per minute. So we use 10 as the mean. But here, we're only looking at a 15-second period. And so that is 1/4 of a minute, right? There's 4 15-second periods in 1 minute. So we're going to adjust our mean by dividing it by 4. So if we average 10 passengers per minute, then we also average 2.5 passengers per 15-second period. Technically, we should put false here because we're looking for exactly 0, but it doesn't really matter in the case of 0 because 0 or fewer is the same as exactly 0. We get the same outcome. So 0.0821. Finally, compute the probability of at least one arrival in a 15-second period. So again, at least one means 1 or greater. So we're going to find the cumulative probability of less than 1, which is 0.0821, right? We would put x as 0. And then find the probability that's greater. We're just going to say 1 minus that. Because again, all of the potential things that could happen, in this case, anything greater than 0 plus the probability of 0, that always adds up to 1. So it wants 4 decimals, 0.9179. So we're saying it's a 0.9179 probability that at least one person will show up in a given 15-second period. Let's make sure we didn't make any mistakes. And it looks like we're all good. All right, finally. Blackjack, or 21, as it's frequently called, is a popular gambling game played in casinos. Players dealt 2 cards, face cards, jacks, queens, and kings, and 10s have a point value of 10. Aces have a point value of 1 or 11. A 52-card deck contains 16 cards with a point value of 10 and 4 aces. So they want to know what's the probability that both cards dealt are aces or 10-point cards. Okay. So we're going to use a hypergeometric probability distribution where we are looking at the probability of successes compared to the probabilities in the population or the larger group. And in this case, if you remember up when we did binomial, we had this issue where we had the same percentage of likelihood in each trial. Whereas with a hypergeometric distribution, we may not. In this case, for example, we have 16 out of the 52 cards being successes if we're looking for 10s, and 4 out of the 52 being successes if we're looking for aces. And so it's a little, these are ways we can help try to identify what type of distribution we're working with. So again, if we come here and we just look at what a hypergeometric, H equals hypgeom.dist, what arguments it needs, you'll see there's a bunch. So it needs sample successes, and the number in the sample, population successes and the number of the population, and then cumulative true or false. Okay, so let me explain what each of those means. So first we'll do sample successes, and then number in the sample, population successes, and then finally cumulative. All right. So our sample successes, well, let's just look at the first one. What's the probability that both cards dealt are aces or 10-point cards? Okay. So in that, out of 2 cards, we're saying what's the probability that both of them are either aces or 10s? I mean, aces or 10s or face cards. Okay. So we're going to say out of drawing 2, we want to get 2 successes out of 2 cards we draw. And in this case, we define the successes as the cards being either a 10-point card or an ace. So the number of successes in the population, well, if there's 16 10-point cards and 4 aces, then there's 20 successes out of a population of 52 total cards. So we're saying is, what's the probability that I get 2 cards that are either 10-point cards or aces out of drawing 2 when there's 20 of those type of cards out of 52 in the whole population? And in this case, we're saying, exactly. So we're going to say false. So our probability is going to equal Hypergeometric samples successes, comma, number in the sample, comma, population successes, comma, number in the population, comma, false. All right. So there's our probability. Wants it to 4 decimals. So again, let's let Excel do the work for us. 0.1433. All right. What's the probability that both of the cards are aces? So now we're saying 2 successes out of 2 cards, but there's only 4 successes in the population out of 52. So you can see that number is much smaller, 0.0045. What's the probability that both of the cards have have a value of 10 points? So again, the population successes will change to 16 because there's 16 10-point cards out of the 52 total cards in the population. 0.0905. Check our work, make sure we didn't make any mistakes. We didn't do the last one yet. So the last one is a blackjack is a 10-point card and an ace, for a value of 21. Use your answers in parts A, B, and C to determine the probability that a player is dealt blackjack to 4 decimals. And then it gives you this little hint, right? It's not a hypergeometric problem. Develop your own logical relationship. So here's our logical relationship. If we're going to say, so the probability that it is, let's just define, so the of A and B, where A is drawing a 10-point card and B is drawing a ace. Okay, so we found here that the probability, oh, not A and B, sorry, A or B. The probability that it's A or B is 0.1433. And then we have the probability that it's B, meaning the probability that it's an ace, is, I guess I should use probability of A for ace. That would have made more sense, huh? 0.0045. And the probability that it's A, meaning a 10-point card, is 0.0905. So if you think about it, if our probability of getting either 10-point card or an ace is 0.1433. And then the probability of getting both aces is 0.0045, and the probability of getting both 10-point cards is 0.0905. If we just subtract out those situations where we get both aces and those situations where we get both 10-point cards, what we're left with is the probability that we get an A and a B, or one 10-point and one face card. So what we're going to do is say probability of A or B minus the probability of B minus the probability of A gives us the probability of getting an A and a B, which is 0.0483. So that's the probability of getting dealt a blackjack, assuming a 52 card deck and that it's not mixed in with other decks or something. Check our work. We're all good. And so hopefully this helps you get through the Chapter 5 guided assignment. As always, if you have additional questions, don't be afraid to let me know. Also, like I think I've said in other videos, we have students from other schools who find these videos and find them helpful. So if you want to like or share or subscribe, any of those things makes these things more visible to other students and helps them, and also let you see when I post other videos that may be helpful to you. I don't monetize. I'm not making money off of this. We're just trying to get this out to people who it's useful for. Anyway, have a great day, and I hope this helps.